Hello everyone, we are starting the last chapter of Algebra 2. This is going to talk about different types of patterns and sequences, and today we are studying Lesson 9-4, Defining and Using Sequences. Our goal for the lesson is to be able to write rules and write terms of sequences and write rules given a sequence. So the first thing that we're going to do is look at a couple of examples. We have pictures, and we're not going to be writing any official rules. So as long as you can tell the pattern, you're going to be able to finish the problem. But I do want you to get used to the notation. So you see how you've got 1, 2, 3, 4, and 5. So what we're going to do is we're going to put an N here to establish which number it is in the sequence, okay? So this is going to be the first number, and that number is going to be noted by A sub N. So the first number is 2 tennis balls. And then we have the second number will be 4 tennis balls. The third number is going to be 6. The fourth number is 8. And the fifth number is 10. So there's a couple of ways that you can kind of go about this. It looks like we are adding 2 to each number. So the first number is 2, and you just kind of look at it and you're like, plus 2, plus 2, plus 2, plus 2. Instead of looking at it like that, I want you to compare this number to this number. So what do you do to go from 1 to 2? 2 to 4. There should be a relationship between these numbers. 3 to 6. Doesn't it look like you're just doubling what number it is? So the first number is going to be 1 times 2. The second number is 2 times 2 is 4. 3 times 3 is 6. 4 times 4 is 8. So if we were going to finish this problem here, it says 10th figure. So instead of us doing plus 2, plus 2, plus 2, we could kind of use a little bit better method and say, I know that this pattern is going to be n times 2. So the 10th number times 2 should give us 20 tennis balls. Okay, so now that we've got that first one out of the way, let's go ahead and look at our second picture. And we're going to put n here. That's going to represent first number, second, third, and fourth numbers, okay? So what we want to do is we want to establish a relationship between the number and the result of that. So the first number has 1 water bottle. The second number has 4. The third one has 9. And the fourth number has 16 water bottles. So we need to figure out a relationship between n and a sub n. So our pattern is 1, 4, 9, 16. While you can establish a pattern between those numbers, one more time, you need to figure out what can I do to 1 to get 1? What do I do to 2 to get 4? What do I do to 3 to get 9? What do I do to 4 to get 16? So if you're familiar with perfect squares, you can kind of immediately recognize that pattern. So what you're going to do is you're going to square whatever number it is, and that will tell you how many water bottles are in there. So the 10th number is going to wind up having 10 squared water bottles, which is 100, and that's a lot. Okay, so let's talk about some really important vocabulary. So I know that you have studied sequences before, ever since you were probably in 2nd, 3rd, 4th grade, but what we need to do is we need to think of it in terms of algebra. So the first thing you want to do, if you don't have it highlighted on your paper, highlight sequence. A sequence is just an ordered list of numbers. Each number in the sequence is called a term. So this 5 would be the first term, second term, third term. So the term basically tells you where the number is, that position in the sequence. Now, this is why we're using a sub n, because that can describe any term in any position. So when you start thinking about this in a more advanced way, algebraically, you need to start thinking about each term as the domain. First term, second term, third term. So first position, second position, third position, and so on. And this Range is going to be the actual number that you see. So the first term, that would be 5 up here, 10, 15, 20, and so on. So you're actually able to graph these. We aren't going to be graphing them today, but we will the next class. Now, what we ultimately want to do is we want to be able to write the sequence as a rule. Now, these are not equations, they're called rules. So as you can see right here, let me make it really big. There's two ways that you can write the rule. You are very familiar with the f of notation. That's just function notation. So if you're looking for the first number, you would do f of 1. You would plug in a 1 here, and you just do 5 times 1, which gives you 5. That is the first number in the sequence. Or you can write it using sequence notation. This is generic for any term in the sequence. So if you wanted the first term, you would say a sub 1, and then if you plug it in, it should tell you 5 times 1 gives you 5, which is the first term of the sequence. So unless it says otherwise, we're going to assume that your sequence begins with 1. But I do want you to be aware that the domain could start, so it may start with 0 instead of 1. But typically, it does begin with 1. All right, let's take a look at the first example. Now, these are the ones that could wind up being on your end of course and on your test. It says write the first 6 terms of each sequence. Now, you don't have to plug it in every time. If you figure out the pattern, then you can continue with the pattern. But I'm going to show my work just for your notes. That way you know how to get every single term. So, unfortunately, there is a little bit of work that has to go into these problems here. So the first 6 terms are going to be a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and a sub 6. All you have to do is plug in the 1, 2, 3, 4, 5, and 6 into n. So it'll be 2 times 1 plus 5. Now I'm just going to continue on this pattern, plugging in the number for each position of the sequence. Okay, if you're really good at mental math, you can go ahead and do these in your head, or you can just use your calculator. I'm going to do the first 3, and I want you to see if you can figure out the pattern. So you've got 7, 9, 11. So the first term of the sequence is 7, second term is 9, third term is 11. Now, hopefully most of you can see it looks like you're just adding 2 every single time. So I'm just going to make a little prediction here. That's 13, 15, and 17. And then we can go back with our calculators and we can verify yes. Okay, so what we're doing is we're just using our brains to kind of figure out this pattern here, but we're using the algebra to actually find the first few terms. Now in section 9.2, we're going to talk specifically about arithmetic sequences. And this sequence is arithmetic because you're adding the same amount to get to the next term. This next example over here is not arithmetic. It actually looks exponential. So that negative 3 here is a base, and your variable, or n, is in the exponent. That means that you're going to be multiplying the same amount to each term to get to the next term. These are called geometric, and that is studied in lesson 9.3. But right now, what we're doing, and this is using function notation, so this would be the first term. We are finding the first 6 terms, and we're just changing the notation out from sequence notation to function notation. But you're going to do the same thing. You're going to plug in a 1 for n, and then this time we're going to plug in a 2, and then just keep going down the line. I know it's not fun, but it's necessary. Okay, so what we have is kind of the work on how we get each one of these. So 1 minus 1, because we got to think, if we're doing this our head without a calculator, we're going to use order of operations. So you're going to do 1 minus 1 is 0, and anything to the power of 0 is 1. So our first term is 1. The second one, that's going to be negative 3 to the power of 1. And then this one's going to be negative 3 squared. So negative 3 times negative 3 is 9. So I'm doing all this without a calculator. You go ahead and use your calculator. That's fine. But right now, if I just kind of get the first 3 terms, I can see that I am multiplying by this base. So 1 times negative 3 is negative 3. Negative 3 times negative 3 is 9. And you can continue that same pattern. So 9 times negative 3 is negative 27. Some of you definitely need a calculator at this point. But all you got to do is just keep using that calculator and you'll verify that you get 81. Oops, skip one, sorry. Negative 27, 81, and then negative 243. You're just multiplying each number by negative 3, and that is what makes this a geometric sequence. Okay, so hopefully you didn't think that the first page was too challenging, but if you're looking for a challenge, there's definitely some challenges on the back of your notes here. What we're going to do here is we're going to write the rules. So you need a really good understanding of patterns to be able to do this, but honestly, if you just practice, I think you're going to get better and better every time you just practice, okay? So don't give up. All right, so we've got a little example here. It says we've got 2, 4, 8. So what you can do is you can just look at that and say, hey, it looks like I'm just multiplying each number by 2. So if you're multiplying each number by 2, what you can do is write an exponential rule. So your base would be what you're multiplying it by, and it would be to the power of whatever element it is. So first term, second term, third term. There's another way you can write this. I'm going to be honest with you. I would never actually come up with something like this on my own. I would probably come up with that first one there. All right, let's do a couple of examples, and then I'm going to let you guys try some on your own. Okay, so what we have to do, first thing that might help you is we're going to write sequence notation next to it. So A sub n is kind of the generic for what number is in a specific position. N would be that specific position. So this is position 1, 2, 3, and 4. That's going to be the same for all of your sequences, except for it might start at 0. I think I've got one that does start at 0, but not this one. Okay. Do we have a relationship between these numbers? This is where you really have to think. What are we doing to 1 to get to negative 1? Well, first of all, I think I'm going to be multiplying by negative 1, but I don't think that's going to be quite it. So if I plug in a 1 here, yes, but if I plug in a 2 here, I only wind up with negative 2, but I'm supposed to wind up with 8. So how can I redo this? Let's see here. I do know that 2 times 4 is 8, but 3 times 4 is not 27. What if I think about powers this time? Well, they're all negative, so I know there has to be kind of a negative here, but I don't know what to put there. So n squared, maybe we'll try squared and see if that works. So 2 squared is 4. It's not big enough. Let's try 3. Okay, 2 to the third power is 8. And then times negative 1 is negative 8. Okay, let's try 3. 3 to the third power is 27. Times negative 1 is 27. Okay, it looks like we've got it. So I just checked it kind of mentally. So we're going to do A sub n, and we're going to put that negative 1 in the front and n to the power of 3. Now, don't worry about it. This one's kind of advanced. So I don't expect you to come up with these like super fast. Okay, so I'm going to start here. I'm going to put my generic sequence, my A sub n here. and then I'm going to put n next to it, first term, second term, third term, fourth term. And what I've got to do is I've got to figure out some kind of relationship between 1 and 0, 2 and 2, 3 and 6, 4 and 12. Okay. 1 times 0 is 0, but if I multiply 2 times 0, I get 2. Yeah, no, that's not going to work. So I can't multiply by 0. What if I subtract? So maybe I could do n minus 1. Okay, so if I plug in 1 minus 1, I get 0. So that works. But what if I plug in 2 minus 1, I get 2. No. I get 1. But somehow it's got to be equal to 2. And that's not going to work. 3 times 2 is 6, but 4 times 2 is not 12. So I can't do times 2. Okay. Let me give you a hint. This one's really hard. So we did come up with the n minus 1. But what if I multiplied it times n? Let's see if this works. Okay. So a sub 1 would be 1, 1 minus 1. Okay, so that'll be 1 times 0 is 0. So that worked. Second term. So that'll be 2, and then I'm going to multiply that. 2 minus 1 gives me 2. That worked. Let's try 3. Now, if the third one works, I think we've got it. 3 minus 1, so 3 times 2 equals 6. So you have to be really clever to come up with this rule. And honestly, it would probably take me several minutes to get here. So don't feel bad about not figuring out this pattern. And if you did, you are awesome. Better than me. Okay. And if it makes you feel any better, I think this lesson's a little bit harder than 9-2 and 9-3. So it is a challenge. I know you understand that this one right here, the 3, 5, 7, 9, yes, we are adding 2, but you need to understand that you can't just say plus 2, plus 2, plus 2. You could do that on the front, but you can't do it here because you have to write a rule. So what you're going to need to do is you're going to put first term, second term, third term, and fourth term. You have to figure out a pattern between n and whatever a sub n is. So how do you go from 1 to 3? How do you go from 2 to 5? How do you go from 3 to 7, 4 to 9? So it's definitely not going to be 1 plus 2, 2 plus 2, 3 plus 2. That's not going to work. So we have to be a little bit more clever in this, okay? So what I'm going to do is I'm going to write down the relationship. So it looks like I'm doing 1 plus 2 gives me 3. 2 plus 3 gives me 5. 3 plus 4. So I've got a pattern here. So what can I do with that pattern to help me write a generic pattern for 3, 5, 7, and 9? Okay, so let's just go ahead and say, oh, you know what? I see a pattern between that number and this one. That's 1 bigger than n, isn't it? 2 plus 1 is 3. 3 plus 4, or 3 plus 1 is 4. 4 plus 1 is 5. I think that's our pattern. So we have n plus 1. Okay, we've got that. So n plus 1 is 2. And then I've got to add this number back to it. So let's see if this works. Okay, let's try 1. 1 plus 1 plus 1 is 3. Yes. Okay, let's try 2. 2 plus 1 plus 2. 2, 3, 4, 5 is 5. Yes. Okay, I got it. That's our pattern. So I'm just going to leave it just like that. I'm just going to say a sub n is n plus 1 plus n. So once again, this is not easy. It's not easy. You really have to think about your patterns, and they're not going to just immediately pop into your head. Okay, so on this one, I tried it. I spent a lot of time on it. And then I realized that n does not start at 1. So this is going to be term 0, term 1, term 2, and term 3. So if you just kind of like run out of ideas, maybe you can try 0 and see if that works. So how can I make 0 turn into 1? I do know if I raise something to a power of 0, I know it'll be 1. So I'm going to go with a power this time. I just don't know what is going to go here. So look at this one here. So if I change this, oh, I don't want to put a 0 here. My bad. I got to put an n. So the first number, I want to put 0. And somehow, so it doesn't really matter what I put here. I can put 100 million. If I put that to the power of 0, it's going to be 1. So let's look at this one. If I raise something to the power of 1, I get -2. So let's put a -2 in here. So -2 to the power of 2 is 4. 3, so it'll be -2 to the power of 3 is -8. That's it. We found it. So once you kind of use that first term to help you start, you've really got to look at that second term. So in case you didn't follow me, if my first position is 0 and the first actual term is 1, then I figured that n would be the exponent. So that was kind of my clue. That's how I got started. The second term helped me figure out what I needed to put in the parentheses. Okay, I'm going to show you a little trick. It's called first difference and second difference. Now, I'm not writing the whole like 1, 2, 3, 4 yet because I'm going to show you something. All right, so 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 5, plus 7 is 17. Now, you see this is called the first difference. If the first difference is the same, it's going to be linear. It's like arithmetic. You're adding the same amount, okay? But this is not the case because obviously 3, 5, 7. But if we do a second difference, so the difference between the first, so I've got a +2 and a +2. See how these are the same? Haha. So what that means is that this is quadratic. So I am going to erase all of this stuff. The reason why I did that is because that is going to help me start my sequence. So I think it's quadratic, which means squared. But if I square a 1, I don't get 2. I get a 1. If I square a 2, I get 4. I'm supposed to make this a 2, and I'm supposed to make this number a 5. So what can I do to the 1 and the 4 to make a 2 and a 5? We're just going to adjust it. We're going to add 1 here and add a 1 here. And then now we kind of get what we want. So if I square the number, I'm like 1 less than where I need to be. So what I'm going to do is I'm going to adjust my rule. I'm just going to add 1 to that to make everything fit. So final answer is going to be n squared plus 1. So right about now, you're probably like scared that you're not going to be able to do any of these problems. Because they've all been pretty hard or challenging. They're not all going to be like that. Don't worry about it. I just want you to practice seeing patterns. So if you don't ever get the answer, as long as you're trying to get there, you are building the reasoning patterns in your brain, and it's going to help you in the long run. I promise. So just stay with me. Okay. So looks like I am adding the same amount every single time. So if adding the same amount, that means that it's going to be linear. It's going to be arithmetic. So it's probably just going to be n. It's going to be times something plus something, but it's definitely not squared, right? Okay, so I'm going to put in 1, 2, 3, and 4. What is the relationship between 1 and 1/2? 2 and 1. Actually, if you just look at the whole numbers, it's kind of easy to see it. 2 and 1. It's not 2 minus 1 because 4 minus 1 is 3. So it's not minus. So do you see what's happening here? It looks like all of these numbers are half what n is. So how do you write half of n? Just like that. So that one really wasn't too bad. So as long as you realize that it's half of n, you can write it like this. If you want to write it like this, you can do it like that too. It doesn't matter. But my final answer is going to be 1/2 n. Hopefully that one was a little bit easier for you. Okay, let's look at the last one. And boy, this one's kind of a doozy. I'm sorry. Okay, I notice a pattern here between each number. So I'm going to do a first difference. That's +5, +7, +9. Okay, that looks like the last one that we did with our first and our second differences. Aha. So our second difference is the same. So that kind of gives me a clue. I'm going to be dealing with something squared. But this is your first term, second term, third term, fourth term. And if I plug a 1 in here, that is a 1. But somehow I have to get to 4. If I plug in a 2, I get 4, but it's supposed to be 9. So how am I going to adjust that? You know what? Maybe I can think like this. Instead of thinking, 1 and 4 and 2 and 9, maybe I can think like 2 to 4, 3 to 9. Because 2 squared is 4, right? So 2 squared is 4, but I don't want the second term to be 4. I want the first term. So I need to change this to, so what am I going to do here? So it's not going to be n squared. What do I need to do to that n? So if it's the first term that I want to be 4, I need to bump that up by 1. So if I add 1 here, so the first term added to 1 squared, that is 4. So that works. Let's try it for the second one. So the second term should be 9. So 2 plus 1 squared, that would be 3 squared is 9. I got it. Okay, so you have to be a little bit clever here. So it's not straight up n squared. You have to take that n and you have to add 1. You have to add 1 to it, and then you square it. So that is your final pattern. So those are some examples. And yes, it takes a lot of time and a lot of patience to actually really, really get good at these, but it is challenging. And sometimes the challenge can be fun. Well, hopefully you're still with me. I promise you that I'm not going to give you something super hard on your test. I just wanted to show you several examples of how your sequences work. There's no telling what's going to pop up on your EOC. So, we'll see what happens with that, but I promise you, you're not going to have anything that difficult on your test. It's going to look more like this apple problem here. What they want you to do is notice that you have a stack of apples, and somehow, some way, they have stacked them in such a way that they are perfectly square for each layer. So let's go ahead and just kind of label each layer. So I've got the first layer here, second, third, fourth, fifth, sixth, and 7. And if you notice, first layer has 1 apple, second layer has 2 in the front, but also has 2 on the side. So it means like 2 by 2, that would be 4 apples total. And then the third row has 3 apples by 3 apples, which is 9. And you can kind of see that there is definitely a relationship between the layer and the number of apples in each layer. So if we just kind of write it down, n is going to be the number of each layer. So first layer, second layer, third layer, and the actual number of apples would be a sub n. So you have 1 apple in the first layer. You have 4 apples because it's 2 apples by 2 apples. 2 times 2 is 4. And then you've got 3 times 3 is 9, which is basically your pattern. So you take this n and multiply it times itself. And we all know that that's just squared. So each layer is squared. So very simple. You don't have to add or take away anything. The second part you need to think about, we are trying to add up to 9 layers, which means that I need an additional 8th layer and a 9th layer. So what I need to do is I need to figure out how many apples would be in each one of those layers. it's really not too bad because we know that each layer is squared. So for the 8th layer, I would say 8 squared is 64. So that would be an additional 64 apples. But then the 9th layer is going to need 81 apples. That's a lot of apples. So for me to get a total of 9 layers using the same pattern, I would just need to add up 64 and 81, which gives me a total of 145 additional apples. So your practice is out of your textbook, but I created a worksheet for you. So you don't need to use a textbook at all. And try to help each other out as much as you can. And thanks for listening.